Hi, Bayesians. I wanted to go over the model plotting, as many of you are starting to get these models to run and now have to make sense of them. The only way to make sense of these models, at least from my view, is to plot their implications. And so I'm going to use the example model here that's model 5.3 in your book, M5.3, that comes from chapter 5. It's the two-variable model. In which the response variable is divorce, the divorce rates in given states, and the two predictor variables that we're wondering if they explain divorce rate are the marriage rate in those states and the median age of marriage in those states. So we've already learned a lot of steps. We open the package, we get the data, transform the data to standardize it, and then fit this model. I'm just going to run through these things real quick. There we transform the data, just copied the code from the book. I've got this model to run, and we can see the model output on the bottom. It's worth getting to know these numbers and trying to make sense of them. But again, to me, the easiest way to make sense of them is to plot them. And the first step in plotting is just to always plot your data. And so we've got a response variable, so we know what's going to go on the y-axis, which is, we can see it right up here in the model. Our response variable is the divorce rate. So we'll put that on the y-axis. And our x variable, we have two of them in this model. We've got marriage rate and age at marriage, median age at marriage. So I'm going to put the age at marriage and just run that. Okay, that's a very simple base R plot. You don't need any extra packages to fit this. And it shows the dots and how they relate. On the x-axis is our standardized variable for age at marriage in a given state. And on the y-axis is the corresponding divorce rate in that state. So just by kind of looking at it, it looks like there's a negative correlation here. We saw that in the book. But what we want to know is how that correlation holds up after we've accounted for marriage rate. So we're going to plot then the implications of this model. In other words, we have data points, but what we really want is we want a regression. We want to know what's the average trend in these data after we've accounted for other things that are in those states, like marriage rate. So from the model, the first thing we've got to do is extract the posteriors. And we're going to do that here with extract samples. Okay, and that generates this object up here, posts, and it's 10,000 samples. We can limit that if we want to, but we'll just keep it as a default, 10,000 samples of 4 variables. The variables are the things that are not data in our model. So up here, D is data, M is data, A is data, but there are unknown things. For example, we've got mu, sigma, and mu itself, we're defining further that it has 3 variables. It's got alpha, the intercept, beta M, the slope between marriage rate and divorce, and beta A, the slope between age and divorce after accounting for marriage rate. And then sigma, which is the average distance that a dot is from the model's prediction. When we extract the samples, those are the 4 things that show up here, right? Those are the 4 parameters that our model is estimating. Where's the intercept? And if we have a value for marriage and a value for age, we can multiply it by these numbers here, the marriage and age parameters, and then draw a regression line. And we've got 10,000 samples, which means we can draw 10,000 regression lines that will come from the posterior. So that's what this code's going to do. First, we extract a posterior, then we set up values to predict across on the x-axis. And the reason it's nice to have a plot is that we can see which values might be reasonable to start with. So the x-axis goes from about -2 to up to 3. So we are going to set our value for I'm going to call it A seek. And we just need two of those values. Let's go to the lowest value on the x-axis and the highest value on the x-axis. If we had this plot and our x-axis value was different, let's say it was 1,000 to 200,000, that's what we would put here. We'd put the lowest value as 1,000, the highest is 200,000. These choices of numbers come directly from what your data are, right? Because we want to see how well the model matches the data. So I've set up this sequence, which is literally just two numbers. You look at it, it's the numbers we put in that C. And I'm going to set up M to be 0. And the reason I'm going to set it up to be 0 is that that's the mean value of M. Once we standardized it, the average value of M is 0. And the definition, what we're wondering is, what's the relationship between age and divorce when marriage is at its average? Like, given an average marriage rate, what's the relationship between age and divorce? Okay, and you can change those numbers, but this is the way to start with looking at these plots of a single variable. Okay, and then I'm going to do mu, which uses the link function. And I've got to give it my model. I'm giving it the posts. So these are the requirements of the link function. It needs to know which model it's working with. We've extracted the posteriors from that model, so we call those that. Had we called these, we could call them anything, but we've called them posts. And so we put that in there. And then we give it data, which is data to predict over, which we've got two things. One is A, which is -2 and 3, and then M, that's our two data predictors that are right here. If we had differently named predictors up there, like C and B, then we would call these C and B. Okay. So what that's doing is it is moving through these posts, and it's filling in a new column on the right here. That's the value of mseek that we gave it, and aseek. So mseek is always 0, and aseek has two values. One is -2, and so it starts with -2 for aseek, and it multiplies that by ba. So -2 times 0.7 plus 0, because that's what we put for M, 0 times 0.27, so that's just 0, plus the intercept value. So I don't know what it would be, but on this row, A plus BA times -2 is going to be about a negative times a negative is a positive, so it's going to be a +1 or something, which on the right-hand side makes sense, because when A is -2, if this is this negative relationship, then the values up here are probably positive. And then it does that again, and then 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 again. Then it does it for the second value we gave for A, which is 3, and repeats the same equation again and again and again and again and again. So we've got 10,000 predictions for what the value of divorce is when age equals -2 and -3. And then we're just going to draw a line between all 10,000 dots. So that's what mu is doing. Then we get our plot back. And our base plot has these dots that we've seen. And the next steps add stuff to the plot, right? So we're going to add those lines. I'll explain this for loop. So this right now, for I in 1 to 50, that's just how you start a for loop. And I is the critical thing. We're going to say what we're meaning is we want this to loop through and calculate the following, which is add lines where the x value is aseek that is -2 and 3. And the y values are coming from that mu. And mu I comma, this stuff here is the first, before the comma is the row. So it says go to row 1 in the posts, that is, go right here, solve that equation, give me a prediction, and place a point up here, wherever that prediction is. Then do it again for a equal to 3, solve that equation, place another dot here, and draw a line. Then do it again. We've got a different set of numbers from our posterior, and then again and again and again. So we've told it to do that 50 times. That is, we've got 10,000 rows. It's going to take a long time to plot 10,000 lines. So let's plot 50 of those lines and see what it looks like. And so this is 50, the first 50 rows, solving that equation, A plus BM plus BA. We know that equation because it's right here. Whatever we would put right there in our linear model equation is what we're solving now. And this is the posterior distribution of the slope between age at marriage and divorce rate after accounting for the marriage rate. If we wanted to plot one line, we could do it like this. There's one line, right? But we always want to plot a lot, because the more we plot, the better we can see both the average trend, which seems to be apparent if you just kind of like go through the middle of these lines. That's the average trend. But we can also see the uncertainty. That is, our model does think that this line here, the lowest line, the most shallow line, has a probability of being the true value, the true slope, if we had all the data. And the steepest line is also a probability, but those are low probabilities of those slopes. The sampler is sampling relative to the probability, and hence most of the posterior probability is on this center line. And in fact, the mean line of that center line, what that slope is it's -0.61. What that means is for every unit increase in A, we decline the value of D on the y-axis by 0.61. So as I move from -2 and go up, it looks like the average y value at -2 on the x is about 1.2. So as I step over to a unit, -1, and I look up, I've dropped on the y-axis, and the value that I've dropped by, I could eyeball it, and it looks like it's about 0.5 or 0.6. I'm not quite sure, but lo and behold, it's right here. This is the relationship between age and divorce rate after accounting for the marriage rate, and it happens to be 0.61. So every time I move a unit to the right, a unit is 0, 1, 2, not 0.1, but 0, 1, 2, 3, 4 integers. Every time I move a unit to the right, it says that divorce rate declines by 0.61. The reason we like to have those numbers and not just the dots is that now, if I'm given an age at marriage of any state, anywhere, and I've got this model, I can predict the predicted divorce rate of any state, anywhere. So if someone gives me a value that says the age at marriage is -1.8, I don't have any data there, but I've got a model prediction that says, well, that tells me the divorce rate is most probably around -1 or around 1, but it could be somewhere between, say, 1.8 and 0.2. Those are called posterior predictions, and we can look at those in more depth. But this is walking through the plotting code just in detail. I will post another video that does the same thing with a different plotting program called ggplot. You're welcome to use any one that you want. The main thing is fit a model, check it out, and get the posteriors. And once you get those, plotting is just plotting, however you'd like to do it.